Yes.
Hello, everyone. Good afternoon. Thanks for the kind introduction, Tanya. So, yeah, I'm Harsha Tadavarthi. I'm a geotechnical team leader and technical manager at MIDAS IT Australia. So, glad to be here representing MIDAS and collaborating with Engineers New Zealand and interacting with engineers in New Zealand. So, it's a different experience. So my topic for today's presentation will be the last one, but it's a basic one as well. So we are going to talk about, I'm going to talk about the static and seismic slope stability assessment via limit equilibrium and numerical approaches. So slope stability is like a pretty common project, like it is part and parcel of almost every project that you guys deal with. It's like around 50 to 60% of the geotechnical engineer jobs as well. So it's a basic one, but very important one. And in terms of New Zealand context, it becomes much more important because of the unique geology that is present in the New Zealand. So these are the contents of today's presentation. We will talk a little bit about New Zealand geotechnical reality. And I will also talk about a comparative study between LEM and FEM. And we will talk about a little bit about earthquake and how GTSNX, which is a MIDAS product that gives and offers solutions for various problems that we face in slope stability especially. Of course, GTSNX can be helpful for other projects as well, foundations, and even the tunneling, and it can be applicable for rock mechanics as well. So yeah, that's the idea. Let's move forward with the first one. The engineer's geotechnical reality. Sorry, New Zealand geotechnical reality. So, like the northern part of the New Zealand, where we find a lot of volcanic ash-related soils, and because of the highly seismic zone of New Zealand, slope stability is essential to be assessed for seismic assessment as well. So these are the major things. I have been traveling to New Zealand for over past year, 1 year, and after interacting with engineers and after interacting with the engineers at New Zealand Geotechnical Conference last week. So this is a very broad idea that I came up with. So highly seismic focused and a lot of weather-driven failures as well. And because it's a highly seismic focused, so liquefaction, lateral spreading are the very important things. And in terms of weather-driven failures, rainfall is the very important part. And of course, the other climate failures, climate-related things like the temperature variations and other things is very important as well. But we will stick to rainfall in this presentation. And yeah, other focuses, other failures such as the rapid drawdown and climate changes effects are important as well. The two pictures that you're seeing right now are the rainfall-driven failure. That's the failure in one of the motorways in New Zealand. And of course, the famous Kaikoura earthquake in 2016. So it's an earthquake-driven failure. There was a fault over there. And we will also see, I was able to create a small model that could represent the Kaikoura earthquake as well. So we will discuss about it in detail in the coming slides. But firstly, when you want to assess the slope stability, so we have various methodologies. The first one is limit equilibrium method. And in FEM, you have two different techniques. Which is the strength reduction method, or shear strength reduction, or C5 reduction. The technique is the same, but every engineer can describe it in various different ways, like C5 reduction technique, or strength reduction method, or shear strength reduction, one on the same. And in the next one of FEM for slope stability, there is one more technique called strength analysis method. So we have all of them in GTSNX. That's the important part, because most engineers deal with LEM, but for important projects, they deal with FEM. So now the guidelines have been enhanced, wherein MBIE as well as NZGS have included the FEM for slope stability assessment in their guidelines. So let's talk about LEM. So it's the oldest and the best known method. So hands down, it's the widest used method for the slope stability assessment all around the world. And the most important thing is, like the name itself suggests, it is limiting the equilibrium conditions. So like most of the things we simplify the failure surface like a circular failure surface, and or we deal with a polygonal failure surface, and we convert this entire failure surface into number of slides, wherein we end up having 5 unknowns. But since we are having 3 equilibrium conditions, there is a need to limit the equilibrium, and hence we have various methods: Bishop method, Felinius, Yambu, Morgenstern Price, Sama, and so on. So this is very in general about limit equilibrium approach, and hence it has own pros and cons. It's very simple to use, and yeah, it has its fallbacks. And when it comes to FEM, so all the things that that we are dealing with LEM, wherein introduction of a slip failure surface or cutting the failure surface into slices is no longer valid. Here, they deal with the strength reduction method or the strength analysis method. So here, as you see in the picture, the right bottom, so that's the Moore-Coulomb failure envelope. For the initial state of the soil, the thick line where you can see the initial Moore-Coulomb failure surface. So for the in situ stable condition, that's how the failure envelope would look like. But as it becomes, as it comes near the failure, it touches the Moore circle where the failure begins. And that's what this strength reduction method or FEM technique does. So it keeps on reducing the strength C and phi. It keeps on reducing the strength and until it finds a failure surface. That's how simple it is. And that failure surface as a result could be a circular failure surface or a planar surface or planar failure surface or a wedge failure surface, depending on the topography, depending on the input material properties and so on. So that's the idea. So it has ability to consider all the equilibrium condition because it's FEM in nature. So since FEM can consider all the equilibrium conditions, compatibility equations, and boundary conditions, and all the constitutive equations, that's the important part here. Most of the LEM approaches or LEM methods are limited to elastic material. But if you want to consider the plastic nature, so the additional strength that you may find because of the hardening behavior or the nonlinearity, so all the additional strength that you may find can only be dealt with the constitutive equations such as hardening soil model or any other nonlinear models. So that thing can only be considered in FEM. So it is a precise method, and it has its own limitations until the previous generation, because we can say it's a highly computationally expensive thing. It can only be used for the important projects. But all those myths can be overcome. So that's what I wanted to talk about as well. So the myths are FEM is too complex. Use it when we have a complex job, and it takes too long for small jobs. So, but it is not the real case. So modern tools like GTS NX, it is user-friendly and intuitive, which makes FEM a go-to tool. No need for like always considering FEM for complex jobs. You can use it for small jobs to complex jobs as well. And since you're going to consider a lot of boundary conditions that may exist in the site, and the compatibility equations, as well as the constitutive boundary conditions, constitutive equations, it helps to reduce field trails that you may end up having after initial trail that you can have from the LEM methods. So it helps to reduce field trace and errors. And computation has been significantly increased. So with the advent of the GPU, as well as multi-core and as well as multi-CPU, like the computation has been significantly advanced over, I would say, last 1 decade. So FEM can be a go-to tool. And according to MBI, the Ministry of Business and in Infrastructure for Engineering, so and NZGS, so they have included FEM in their slope stability guidance as well in the October 2024 draft. So it is set to be released, I guess. Yeah. So these are some of the myths, and the facts is, yeah, you can go with FEM very frequently and for small to complex jobs as well. So I wanted to highlight some limitations that we have with FEM and what we can deal with that FEM as well. So comparative study has been made. So I created a very simple slope. We have dense soil, and the bench is like around 45 degrees, and cohesion of 30 kilonewton per meter square, friction angle of 36 degrees. The elastic modulus was wrong over there. The elastic modulus that I considered was 50,000 kPa. So this is the simple slope for the comparative study I created between LEM and FEM. So what we found is, in the case of LEM, we found the factor of safety to be 1.78. And the same thing has been found in FEM as well, 1.77. The strength reduction method has been applied. So the idea is, for a very simple slope and a uniform soil throughout, you would end up having the same failure surface and the same factor of safety, so which is not a concern at all, right? Both approaches are giving the same onset. And when you go over the earthquake, even during earthquake assessment, wherein in this condition I had considered the pseudostatic assessment, the horizontal seismic coefficient as well as vertical seismic coefficient has been provided. For this, I had considered the PGA of Kaikoura earthquake, so it's 0.22 G, and the horizontal coefficient has been considered like 0.5 times of PGA, which comes like 0.5 times of 0.22. And the horizontal coefficient was that, and vertical coefficient was considered like 2/3 of the horizontal coefficient. So that is what considered in this assessment. And we end up having almost same result for limit equilibrium approach as well as finite element approach, because the soil has been uniform and all the other things. But yeah, it is the same thing that you would find in the uniform soil and very simple slope. But what if, for very simple slope, the FEM and LEM are providing very same results, not similar, it is the same results exactly. But what if we have complex slopes with multiple soil strata? So sometimes there might be a very thin layer, which is liquefiable in nature, and that is providing and challenge for the engineer, like maybe who might be dealing with pile foundation over there, or who might be dealing with slope stability. So thin layer could be of a very important concern for many engineers. So what if we have a very complex slopes with multiple soil strata? Is LEM going to be helpful there? So we will check it out. Also, if you're dealing with a soil and fractured rock, so if you're dealing with a fractured rock, it is explicitly needed to model it, or else at least needed to consider the rock mass properties. So is LEM going to be helpful for that? So we'll find it out. And what if rainfall, a transient state, is to be considered? So the regular LEM approach, it considers the steady state condition. Of course, we run the seepage assessment in the transient, but at the end of the day, we take the final steady state condition to the LEM analysis and run the assessment for the slope stability. It is a kind of steady state condition, but you have a transient condition need to be considered at regular intervals. You would like to find the factor of safety because the stress state changes because of the rainfall. So what if you want to consider the rainfall, a transient condition, and how it is going to affect the stability of the slope? This is one more thing. And what if you have a cyclic moment during the earthquake? So what happens is during the earthquake, since it's in a sloping ground, there will be accumulated displacement because of the cyclic movement of the ground. So whether it is possible to consider in LEM, it's not, because you would not find displacement in any LEM approach. It's just providing you the factor of safety and the probable failure surface. So earthquake triggered lateral spreading and liquefaction needed to be considered as well, right? So if you're dealing with lateral spreading, and if you're dealing with the liquefaction, it is a governing thing here in New Zealand, right? So we need to consider FEM only for this approach, because in LEM, there are many assumptions that need to be considered by changing the material properties via various empirical equations to be able to understand the effects of lateral spreading and liquefaction in the slope, right? So again, FEM will be a better approach. We will see what we have in our pockets for considering all these in GTSNX, which is our geotechnical product. And How about multiple shear failures or progressive sequential slope surfaces? So what happens in reality is whenever, let's say, you're dealing with a volcanic ash and there is a lot of rainfall and the phreatic surface has been increased dramatically and you end up having fully saturated condition. So the failure surface may not no longer be a circular failure surface. There will be sequentially failing happening. That means one failure surface followed by some other failure surface and so on. There will be a progressive nature of development in the failure surface, which can never be considered in LEM, of course. So what FEM can be, where FEM can be useful for sure. So let's check some of it. And also, what if joint plane and the tension cracks in the rocks are to be simulated? Yes, again, FEM could be helpful in this regard. So let's check the same for slope instability or slope stability assessment in volcanic ash soils. So this has been taken from one of the recent project from one of our clients. So I would like to thank him for providing the data. So let's talk about this particular slope. So we have an Enger ash and Hamilton ash, upper Matua and so on, lower Matua, and we have a weak layer in between. So this is the soil strata as well as geology that has been considered in this study. So if I go with the just self-weight of the soil and find whether the slope is stable or not, I'm ending up finding LEM to be not stable. So you are finding the factor of safety less than 1. So it is unstable. But of course, when I go with the FEM approach, so I am ending up having a factor of safety of 1.23. This is just under self-weight, no rainfall, just the initial water level condition. And you can see the initial water condition, which is well below the sloping ground. So here, there might be a lot of reasons for the increase in the factor of safety. So the reason could be a consideration of the plastic nature or of the soil. So consideration of the non-iterative iterative scheme of the nonlinear solver in the FEM. So there can be many reasons, but the idea is, yeah, the factor of safety is not same as the factor of safety that we find from the LEM approach. So we have the factor of safety of 1.23 here for the complex soil strata that we have now. And how about the rainfall? So the interesting thing happens here. So if you see, because of the rainfall, the initial water level, which was well below the ground, is now almost reaching the ground over there. So that the picture on the left top, you can see that raised water level due to the rainfall. And the rainfall was applied on that surface as a boundary condition. That's the transient condition was considered in this case. So due to that, when I run the slope stability assessment, I could able to see there are multiple failure surfaces getting generated. So you can see the failure surface at the toe or the face failure on the top, and there is a circular failure surface generating in between in the middle, and there is a bigger failure surface which is passing through the thin layer over there. So all these things can only be considered in FEM because you would able to find the progressive or sequential failure surfaces which are developed due to rainfall, and the factor of safety over here is like 1.05. So under self-weight it was 1.23, and under rainfall it now is 1.05. So it has been reduced. So which is an important fact for volcanic ash soil, because in the volcanic ash soils, as and when it becomes saturated, it becomes it starts failing. And this is how the pore pressure distribution that you would find in FEM. So because of the seepage assessment and how that seepage assessment is going to affect the stress condition and so on. So the increased phreatic surface on the left top, and the right bottom is the pore pressure distribution. So you can see the pore pressure distribution is varying significantly throughout the slope because of the topography and rainfall and infiltration properties, permeability, hydraulic conditions, basically. And coming to the next important part, the tension cracks. So this is one of the very random profile that I had. I was able to get it out from the internet. So this is for one of the like a Kaikor earthquake condition, and this is the slope for that. And here I was able to model the entire joint plane, and there was a sedimentary rock and there was a gravic rock. And because of the modeling of the joint plane, I was able to find the failure surface mostly situated only in the sedimentary rock. And even that, as you can see, multiple failure surfaces developed over there because of the tension cracks that are being generated. So it is it is like one part of the sedimentary rock being failing and followed by the other part, and so on. So the right bottom like GIF file can help you out in better understanding of the tension cracks that could have been developed because of the joint plane in the sedimentary rock. So this is one such example, and this can only be developed in, again, FEM. So coming to the earthquake, so seismicity is a very important part in New Zealand. And most of the times we end up dealing with pseudostatic method for the slope stability assessment here. And here we go. So because of the pseudostatic assessment of this very simple slope that I had carried out, we in LEM, we found like 1.5. But again, sorry, in FEM, considering the strength reduction method for a pseudostatic method, I found the factor of safety to be 1.5. But instead of considering the pseudostatic method, how about considering the time history assessment? That means you're considering the entire ground shaking. So again, New Zealand guidelines is asking you to go with shaking whenever it is needed. So ground shaking analysis need to be considered again up to the users or the geotechnical engineer interpretation and discretion. So for the ground shaking, for the same model, I was able to find the factor of safety of 1.02. This could be due to the amplification of the signal that is traveling from the bottom layer to the top layer, or this could be due to the all the accumulated displacement that you could find. So here we go. So there was an amplification. You can see the red color dot is the amplification, amplified signal, the red on the left top picture. So basically, in this particular case, I was able to assign the Kaikour earthquake, and I was able to. It was generally the Kaikour earthquake was so severe. It was for 120 seconds. The ground shaking happened for 120 seconds. So I was able to assign only for 40 seconds for quick assessment in this simple analysis. So I was able to find the amplification in the ground, and the right bottom is the accumulated displacement versus time. Since the slope is not confined on the other side, we were able to find the accumulated displacement that was happening because of the ground shaking. And yes, the result is the factor of safety reduced from pseudostatic assessment of 1.5 to the ground shaking assessment of 1.02. So this is, again, one particular study wherein time history has its own implication, and it is necessary at least to consider for the important structures. So that's in general about the challenges and what kind of failure mechanisms that we could find from the slope stability and how FEM can be helpful in that regard. Now I would like to talk about the solutions that we have in our pockets, which is GTSNX. It could be helpful for both the large and small slope stability assessment. So let's see what we got. So initially, as I said, LEM is an important part. And this package, GTSNX, can help you out in finding LEM analysis, FEM analysis, both 2D and 3D under one platform. So which is very much important because even though if we want to go with FEM, it is always needed to start with LEM, right? So LEM is like an initial step. You understand the behavior, you understand what is the failure surface and the corresponding factor of safety and where it is exactly happening. And it is better to assess it with FEM depending on the nature and the requirements of your project. And thereby you will end up doing either 2D FEM or 3D FEM. And you can do everything under one platform. That's the important point. No need to get into different licenses, just one platform, all the approaches. And the other thing is, in the case of soil, construction sequence is very important. It is a case with every other project, but it's much better, much important in the soil situations because soil is a highly nonlinear material, right? So because it is being a highly nonlinear material, as a stress changes, that means as a construction sequence changes, its behavior changes right? As the stress changes, the behavior changes, and thereby the nature of the soil could change from elastic to plasticity at any given point of the time, depending on loading or unloading situations that is happening in the site. So here in this software, of course, you can consider all the construction sequencing, and you will be able to find the factor of safeties and the failure surface for each and every stage for a particular local assessment or a global assessment. Yeah, this software offers you the SRM for construction sequencing as well, or the slope stability assessment for construction stages. And the next thing is, now, yeah, we are able to find that the slope is unstable. So what do we go with stabilization? There are various ways, like you can deal with soil nails, rock bolts, piles, or maybe geogrid. So geogrid, again, has been becoming a more abundant for slope stability assessment. So yes, we can do provide geogrid in this software. The important thing is, geogrid being only tension-only element has to be implemented in such a way like being, it should be able to only take tension, no compression at all. So instead of modeling the geogrid as elastic material, it should be modeled as a tension-only material, wherein it can only take in tension, and thereby you can see how the factor safeties are changing because of it taking only tension, and you will end up finding what is the axial force coming in the geogrid. So if that axial force, basically the tensile force, is greater than your manufacturer criteria or not, we can end up having an idea, and then we could see, okay, geogrid is not failing or failing. Yes, so we have an geogrid which is a non-isotropic material and tension-only material present in this software for stabilization of the slope, or even MSE walls as well. And another approach I was talking initially, right? So the another approach in FEM is the strength analysis method. It's a kind of hybrid method. So it was developed in the late 1900s. And yeah, what happens over here is you're still dealing with the slip circle surface, but instead of considering the Bishop method, Felonius, Yambu, Mogisham, Price, and so on, it considers the FEM approach for calculation of driving and resisting forces. So it's one of the interesting approach and has been getting popular nowadays. And yes, we do have this approach in this software for so long. So you can still consider slip circle surface. You can provide the area of interest that you wanted to analyze, and you can still find the consideration of the plasticity nature of the soil because you're dealing with FEM analysis. And the important part in New Zealand, again, we need to consider the seepage effects, basically, which could be like back related to your rainfall. So it is needed to consider rainfall, and thereby how the rainfall is going to affect the stability of your slope, and thereby how your slope factor of safety is changing. So here is one example. So without seepage, you're finding around the factor of safety of 2.45, but with seepage effect, you can see the factor of safety of 2.1. This is the earthen dam situation. On the upstream side, you have the water level. So because of the water level, there was hydrostatic force working on the dam. And because of the seepage movement from upstream to downstream, you can only find the failure surface getting developed only on the downstream, not on the upstream side. So if you are doing a rapid drawdown condition, there is a possibility of finding the failure surface on the upstream side as well. So both can be assessed in the same software, but it has to be integrated with flow and a mechanical behavior. So we have an opportunity to consider flow and mechanical coupled analysis using this software. And MSE walls. So MSE walls where the geogrid and the fascia plates need to be modeled. Yes, you can actually consider all the geogrids as well as fascia walls and the construction sequencing, and you will end up having the factor of safety assessment can also be done. So yes, we can deal with MSE walls as well. And dynamic slope stability, which is, again, a very important part here. And I already covered a small study on dynamic slope stability when you want to consider both pseudostatic as well as dynamic slope stability with SRM. So here, we have an interesting analysis called time history assessment plus SRM. So you can let the software analyze for ground shaking. Maybe you will end up having a 20-second earthquake to be inputted to the software. And maybe in that 20 seconds, you can ask the software to analyze the slope stability at 15th second or maybe 20th second as well. So you can let the software know at what point of the time during the earthquake the stability of the slope is. So this is one interesting thing wherein it could be applicable for any kind of slope, and even not just seismic load, but you can apply for other kinds of dynamic loads like the terrain dynamic load here. So the terrain dynamic load, the terrain is moving and how the embankment failure is happening. So not just seismicity, but other dynamic loads can also be considered. And liquefaction, again, the important part. So in the case of liquefaction, the pore pressure development and at the same time how the shear stress reduction is happening, that is important. And we can consider that using various constitutive models in this software. So we have UBC SAN as well as PM4 SAN, which can help you out in accumulation of the pore pressure ratio that you're finding here, and how the layer is going to have no strength at the end of the day because of the liquefaction, and how the pile's behavior will be changing with respect to time can easily be assessed here. So this will be very much helpful for detailed assessment of maybe a simple building or maybe a bridge or maybe for slope stability assessment. So could be of any condition. So you can assign all these materials and maybe ask the software to assess the slope stability at any point of the time. And consolidation plus SRM, since soft soil is also predominant in New Zealand, so maybe consolidation, long-term settlement might be very important in many parts, maybe for motorways or embankments and different situations. So we can model the consolidation, and we can also go with the ground improvement and see before and after effects of consolidation on our ground improvement techniques on the embankment. So you can see what is the failure surface and the factor of safety before and after ground improvement on the embankment. So even this kind of situation is possible in this software. So to do all these things, we need to have a proper modeling tools, right? So you wanted to create a simple slope. Yeah, you can directly create and using the AutoCAD related functions in this software. Otherwise, let's say you wanted to create a 3D slope. So we have many features for creating the terrain model for the large slopes. So suppose you're dealing with the hilly terrain, you can take into the contour data or maybe LiDAR survey data, so the elevation data, that can always be converted to a surface, which is a terrain. And later on, you can always import the borehole data to get the soil profile or strata developed in this software easily. So previously, again, modeling is the important part, but takes a lot of time initially. But due to the advancements in the modern tools, the modeling has been made easy. And at the same time, the computation has been increased. So yes, it will take a greater time when you compared with other LEM tools, but yeah, very less time when you compared with the previous generation of FEM tools. And of course, instead of just contour data, you can take into the LiDAR survey or elevation data and convert that to a surface, and that can be obviously taken back to a 3D model. And instead of modeling, you can always import all these files. So every other consultant might be using different software. Some might be using Leapfrog, some might be using Civil 3D, some might be using other softwares. You can import all those models here. Thereby, you will be able to create the assessment for slope stability or any other profile. So we have all these options available to import various model files. And if you are dealing with a block model, even block model can be inputted as a direct mesh. You can completely ignore the modeling definitions of geometry. Simply import the block model, which will help you out for the creation of the direct mesh in this software. So even this kind of interoperability is present. And of course, this can be helpful for landslide. So once the 3D model is developed, you will be able to create this kind of landslide assessment. So instead of simplifying this slope to a 2D model or a 2D profile, it's always better to consider a 3D profile in these big, large slopes because of confining stresses is very different in 3D model or when you compare with a 2D model. And lastly, now you went with a 3D model, but when you consider FEM, you will end up having a failure surface in a global area. Maybe that area it will be of no interest for you, but you can still consider the local slope assessment. You can just select the area of interest, and you'll be able to find the factor of safety in that particular area. So in area 1, you wanted to find the factor of safety. In area 2, you would be able to find the factor of safety. So all these things can be done in a single model, both local as well as global slope assessment can be done. So yes, that's the idea from today's presentation. So yeah, happy modeling. If you have any questions, I'm happy to answer.